Okay, so we have another problem where we're going to use dimensional analysis. In this case, what we're asked to do is combine three fundamental constants of nature. C, the speed of light, which tells you when effects from special relativity are important. Newton's universal constant of gravitation, which is the coupling constant for gravity, so that tells you when general relativity and gravity are important. And Planck's constant, h, and Planck's constant sets the boundary between classical physics and quantum physics. Those three constants of nature can be combined in a unique way to give you a length, which is called the Planck length, or a time, which is the Planck time, or a mass, oddly enough called the Planck mass. In this particular problem, we're asked to find an expression for the Planck time. And then the meaning of this is on time scales shorter than the Planck time. So for example, if you set clocks to start at t equals 0, it's not meaningful to take the laws of physics that we know at present and ask about a time closer to 0 than the Planck time. As we're going to see, it's a really small time. So our current laws of physics are in pretty good shape, but we know at some level there has to be some reconciliation between general relativity and quantum mechanics to give a complete picture for quantum gravity. So this sort of tells you what boundary that will be at. All right, so let's get started. This problem is a little bit more involved, and part of the reason for that is this is going to give us a chance to practice solving a set of simultaneous equations, which is going to be a good skill to have further down the road in the class when we deal with things like equilibrium structures. All right, so what we're saying is there has to be an expression where I have on the left-hand side the Planck time in seconds that is going to be made up out of Newton's universal constant of gravitation, and I'm just going to put in its units. So that is Newton meters squared per kilogram squared, and g could be to some power alpha, which we need to find. I have the speed of light, which is in meters per second, and c could be raised to some power beta, and then the last term is Planck's constant h, which is a joule times a second for its units, and that could be raised to some power gamma. So I went straight into the Greek alphabet here because I didn't want to use like A, B, C, because C is also used for the variable for the speed of light. All right, looking at that, Newton, the unit of force, is a composite unit, so we need to break that down into its base units in terms of kilograms, meters, and seconds. Joule, a joule is a Newton times a meter. That's a unit for energy in MKS. And again, that's composite, so we need to break that down into kilograms, meters, and seconds. So this next line, that's what I'm going to do. And there'll be a little bit of simplification. So a Newton is a kilogram times a meter over a second squared, and then I still have a meter squared and a kilogram squared, and that all could be raised to the power alpha. C meters per second, that didn't change. And then I'm going to break a joule down into its base units. And a joule is a kilogram meter squared per second squared, multiplying that by the second. So there's a little bit of simplification. I can get rid of 1 power of the kilogram, and I can eliminate 1 power of seconds. So let me just clean that up a little bit. Copy it down. I have meters cubed in the numerator and kilogram seconds squared in the denominator. And for h, Planck's constant, kilogram times meter squared over seconds. To the power gamma. Okay, so this is actually a set of 3 simultaneous equations. One of the equations is looking at just the power, or all the terms that have meters in it. There are no meters on the left-hand side, so I know on the right-hand side I can't have any meters. For seconds, I'm going to have seconds to the first power on the left-hand side. So all of these terms that have a second in it, those are going to have to give me second on the right-hand side. And then lastly, for kilograms, no kilograms on the left-hand side. However, I combine these, I'm going to have no kilograms on the right-hand side. And so I have 3 simultaneous equations, and there are 3 unknowns, alpha, beta, gamma. So I can solve that set of simultaneous equations. So let me label them. So the first one is when we just look at the meters. There are no meters on the left-hand side, so that's m to the 0 power. From this term, I'm going to get m to the 3 alpha. I'm going to get m to the beta from the second term, and then the last term is going to give me m to the 2 gamma. My second equation, the one that involves seconds, seconds to the first power, is going to give me, I have a seconds to the minus 2 alpha from G. I'm going to have seconds to the minus beta from the C term, and I'm going to have seconds to the minus gamma from the H term. And my third equation in my set, no kilograms on the left-hand side, so kilograms to the 0, and that has to equal kilograms to the minus alpha, because kilograms is in the denominator. No kilograms from C, so that doesn't make a contribution, and I have kilograms to the gamma. Okay. And looking at just those equations for the exponents, this tells me that 0 will equal 3 alpha plus beta plus 2 gamma. 1 has to equal minus 2 alpha minus beta minus gamma. And then from equation 3, 0 has to equal minus alpha plus gamma. So that equation 3 immediately tells us something that tells us that alpha equals gamma. I'm going to take that information, and in solving this set of equations, I'm just going to substitute that into equation 1 and then equation 2. So let me rewrite equation 1, substituting in that gamma equals alpha. That tells me 0 equals 3 alpha plus beta plus 2 alpha. And equation 2 now reads 1 equals minus 2 alpha minus beta and minus alpha. So let me clean that up a little bit. Rewrite equation 1 again. 0 equals 5 alpha plus beta, and equation 2 tells me that 1 equals minus 3 alpha, and it is, minus beta. Okay, so looking at that, those are two equations and there are only two unknowns. I can solve that. Probably the easiest way to solve that is just add the two equations together, because then beta cancels out. So if I just add equation 1 to equation 2, that's going to tell me 0 plus 1, usually 1. 5 alpha minus 3 alpha is going to be 2 alpha plus beta minus beta, means beta cancels out. That tells me that alpha, which is equal to gamma, is equal to a half. All right, so now all we have to do is solve for beta. We can do that by setting alpha and gamma equal to half in equation 1. And that's going to tell us that we have 0 equals 5 alpha plus beta. Substitute in alpha equals a half. Therefore, 0 is going to equal 5 halves plus beta. And that tells us that beta is equal to minus 5 halves. So there we have all three of our exponents. Alpha is a half, gamma is a half, beta is minus 5 halves. Okay. So I warned you this one's a long one. We're on to the second page. Try to be a good physicist, and knowing my limitations with algebra, I'm going to double check that I didn't make a mistake. So I'm going to go back to equation 2 and just make sure I get the same answer. So equation 2 told me that 1 equals minus 3 alpha minus beta. So let's check that when we put in our solution. 1, that was equation 2, sorry. So 1 equals minus 3 halves minus 5 halves. So 1 equals minus 3 halves plus 5 halves. And yay, we're happy with that. Okay. So we've done all this work. We now have the exponents alpha, beta, and gamma to make the Planck time. So let's go ahead and do that. So the Planck time is g to the alpha, alpha is a half, c to the beta, so c to the minus 5 halves, and h, the Planck constant, to the gamma, which is the half. So that looks weird. It's not the way we'd normally write this out. So everything is with a square root. So what we have is g times h upon c to the 5th, all square root. So let's go ahead and throw in our numbers. Now we're here at the end and see what our answer is for the Planck time. So G 6.673 times 10 to the minus 11 meters cubed over kilogram second squared. H is 6.626 times 10 to the minus 34. That in base units was kilogram times meter squared over a second. And in the denominator we have the speed of light, which is kind of fast, to the fifth power. 2.998 times 10 to the 8th meters per second to the fifth power. And that is all square root. You put that into your calculator. You'll arrive at Planck time. So I've got 4 digits in everything. So my answer for the Planck time also has 4 digits. 1.351 times 10 to the minus 43 seconds. Now let's double check that unit. Just to try to be careful. In the numerator, for meters, I have meters cubed, meters squared. The denominator is meters to the fifth. So all of that is going to go away, which is our hope. Kilograms cancels out. Kilogram, kilogram. I have, it is going to be, once I flip everything around, it would be seconds to the fifth in the numerator, seconds cubed in the denominator, and I am going to take the square root, so the square root of seconds squared is in fact seconds. So there we go. It even has the right unit. And that is a time, the Planck time. Then the meaning of this very, very, very amazingly short time is on time scales there and shorter, we would need to have a quantum theory of gravity. If you're concerned with something that's longer than roughly 10 to the minus 43 seconds, perfectly fine to use our current set of laws of physics.